Good morning, everyone, and welcome to XJet's first ever webinar to the European AM audience. Our topic for today is the story of 10,000 parts. And in this session, we're going to introduce in details our technology, our process, and most importantly, we'll show you how a part is made out of our print wash sinter with shortened lead time and industrial capability. So before we start the session, let me introduce the flow of the session today. We will start the session with Andy Middleton, the VP Business of Europe at XJet. He will share with you our company and also the market of ceramic and metal AM. Following that will be Stefan, the Business Manager of Europe. He will share about our product and our process and guide you through a brief understanding of how the system works. And most importantly, it's going to be followed by a virtual tour, an immersive virtual tour to our AMC center, where Ron, the team leader, will show you from the moment where we started the printing, started the file preparation, all the way to a final part status. So this is the brief flow of the conversation of the session today. And of course, followed by the virtual tour at the AM Center, we'll also show you how business-wise our solution is better in terms of the business potential, about the cost, and about how applications can be really made big with our solutions. So I will stop here and I will pass the floor to Andy Middleton, the VP Business of Europe, and he's gonna give you a brief understanding of how XJet and how the market is giving us the golden time, the golden opportunity. So Andy, the floor is yours now.
Good morning, everybody. Welcome to XJet. A real pleasure to see so many participants who've taken the time out of your probably busy agenda to come and join us. Thanks for the introduction. And I'm going to walk you through, firstly, with quite a bold and big statement, which is everything that can become digital will become digital. And in our case, the manufacturing is no exception. And with that, welcome to XJet. Additive manufacturing. I've had the pleasure of being within this industry for over 15 years now. And when the industry started probably 30 years ago, people were trying to figure out how to extrude plastics and make prototypes. And basically 30 years ago, a 3D printer was just about capable of producing 2 or 3 or 4 parts a day, and were generally used for prototyping. Fast forward over the last 15 to 20 years, what we've seen now is a multitude of different technologies entering the market and a multitude of applications growing across multiple industries, from healthcare to aerospace, to electronics, to sensor technology, to healthcare, biomedical applications. It's become a big thing, and companies have been investing billions of dollars over the last, as I said, 10 to 15 years to fuel this additive process going forward. Additive today is, if you look at the total manufacturing business around the world, which is estimated to be approximately $16 trillion annually, additive manufacturing takes up approximately 0.1% of that. But let me put it into perspective about how it's going to be growing. Today, if you look at the numbers which analysts and research institutes share with us, we can see that the additive manufacturing business within the whole manufacturing business today is estimated to be around 72 to 75 billion in 6 to 7 years' time. If you look at the red portion of the square that you're looking at, what you can see there is that within metal, that's going to be taking a lion's share of that market. Ceramics, bottom left, is today the smaller part of that market. Now, my experience with analysts and research institutes is that one thing they all have in common is that these numbers are wrong. These are estimations. The most important thing is the growth which is going to be taking place, and these they normally are able to pin down quite accurately. In 2022, metal and ceramics are going to be looking to grow over 20% going forward to 2030. The expectation is that compared to today, where there've been 3,000 systems that have been sold, that's going to be growing to somewhere around 16, 15, 17,000 in the next 6 to 7 years. The message within this short intro is that many of you who've joined the call today are already in additive. Many of you are considering getting into additive. And this slide and these figures should enable you to gain confidence that additive manufacturing will be a large part going forward of a multi-trillion-dollar industry. And over the years, we believe metal and ceramics are going to be fueling the biggest growth. Where do we play a part at XJet? We're a company here where I'm physically located right at the moment in Israel. We started back in 2014. We have put millions and millions of dollars into the research and development. We're working together with 100 employees. We have 80 patents to our technology. This is the core, this is the heart of our product, is the technology and the patents surrounding it. We've managed to gain leading customers in the additive production of ceramics and metals around the world. And some of those customers are brand names that you will surely have heard of. Why have we managed to do that? It's all around quality. It's about having a system, the only system for additive manufacturing that is genuinely not limited by geometries. And the reasons for that is what Stefan is going to be sharing with you in just a moment. But this high-level statements only really start to become realistic and understandable if we look at a particular part that you or your customers may want to have manufactured, which can't be manufactured today. The part that we're going to be discussing, this is a visual of it. It's a multi-input industrial nozzle used for the blending of chemical materials. It may sound, okay, that's pretty simple. It's not. The challenge is that this specific geometry had to be designed for additive, otherwise it would not be possible to manufacture. We have spent time and effort over the last months and weeks and looking at this part and saying, how many can we actually produce and what are the real challenges? The challenges are, we need high resistance to heat, abrasion, and chemical corrosion. We need to deal with very complex internal structure with channels, and we need to have extremely smooth inner channel surfaces to allow these chemicals to pass through freely. And on top of that, the client who's using this particular product requires at least 10,000 of them. So we took on the challenge. We included it into our process. We printed it on our system that you're going to see very shortly. But to understand how we actually do it, I would now like to hand over to Stefan, who will walk you through the technology so you can really get a deep understanding of why only XJet is capable of producing this part in these quantities. Stefan, over to you.
Thank you very much, Andy. Thank you very much, Yael. Hi, everyone. Yeah, I'm also happy to have such a small crowd here on this tour. My name is Stefan, and I will be your guide today on how the nanoparticle jetting or NPJ technology works. Just a glimpse. It's just an overview of what we are capable of doing and how it will finally benefit you if you use it for yourself. So the official term of nanoparticle jetting, the more public and official term, is direct material jetting. And this jetting technology is, as Andy just mentioned, it's unique in our material environment. So for metals and ceramics. And of course, it comes with certain features and their advantages that will either lead to an absolute fantastic part or final part end use quality, or they lead to the possibility of printing tens of thousands or even hundreds of thousands of parts with only one machine and one full-time operator, or even less than that. So these features you can see here. You can see nanoparticles ink, water-soluble support, etc. They will be the roadmap for the next 5 to 10 minutes of my presentation, before I then hand over to our fantastic team in the Additive Manufacturing Center and Ron to present the real deal. So we have the nanoparticle ink, which is, in our case now, alumina, zirconia, or stainless steel 316L. We have our unique water-soluble support, the high-resolution printing, and the result of that, the high-quality end-use parts. And I will start now with the nanoparticle ink. So the basic principle is we use a special liquid or ink in a cartridge, and we jet it onto an empty and heated tray. It is comparable to an inkjet printer in your office, but the overall technology is much more sophisticated and advanced. So this ink that I just mentioned, it contains particles of ceramic or metal in a sub-micron size that will, during the printing process, start to build up and then will finally lead to your final green part. And as I mentioned, we have a liquid dispersion. We don't have loose powders. We don't have slurries. So you don't have to have, you do not have these complex handling processes or safety measures that you have to take to keep your environment healthy and safe. But also, because of the size of the particles, we create a much more ecological sinter profile, which means we can consume during the sintering, for example, less energy, and the sinter cycles are shorter, which makes this process productive, especially when it comes to the end-to-end, from the end-to-end view of the whole process. So the water-soluble support, and I can tell you for most of us, or I think all of us at XJet that present our technology frequently, this is the most exciting one. It's the most exciting feature to present and speak about because it has the biggest effect on the productivity of the whole MPJ process, even though, because of its support and so on, it seems like it's very focused on the potential increase of geometries and so on, which it does, but it has not just this advantage. So basically, we print two materials in parallel. We print the support structure and the build material. And this printing of two materials in this high resolution at the same time gives us the possibility to create absolutely complex structures because we have absolutely complex support structures that we can potentially print. So this does not only lead to very, very complex geometries, but because the support material is water soluble, we now can create parts very much such as the one that Andy just showed you here on the bottom that have inner cavities, inner channels, and inner complexities. So what we call a real freedom of design. But on top of this geometrical and design aspect, we have the aspect of this water-soluble, fully automated process. We have a device, our smart station, that gives you the chance to remove the support structures fully automatical during the night, during a weekend, or in parallel to another print job. So this is the absolute fantastic baseline for a technology where you can grow over proportionally with parts output to labor. That's why what I meant with you can probably even use less than one person, one full-time person to operate one system. And we estimate that you can operate up to 3 systems in parallel with one person. Of course, also reducing the necessity of having shifts, as you can print during the night, you can wash during the night, or in parallel to weekends and whatever. This gives us a fantastic scalability. High resolution jetting. We are printing at 1,440 drops per inch in terms of resolution. We are printing 120 million drops per second maximum. And we are printing in very thin layers of at around 8 micron. And this high precision and high resolution leads, of course, to the potential of printing very small details and also printing highly accurate. But on top of that, we can create with these nano or submicron particles and the precision, we can create a density of more than 99.95%, which on the one hand lead to fantastic mechanical properties of the part that are comparable or sometimes even better than traditionally made ceramics or metals. And this all results into what we call end-use parts. And why we consider them end-use parts and why we think this is true, I will show you here on this slide. So we can print details, as I mentioned, inner channels and so on, down to a level of 200 microns. We can create smooth surfaces with an RA value of 0.8 to 3.2 in ceramics and 0.8 to 6.3 microns on metal. Additionally, we can create highly accurate parts of plus minus 50 micron that enable us to print pre-assembled parts that can even move and are also end-use parts, for example, in the medical surgical environment. And now the last advantage is our density. For ceramic, we can create a density of more than 99.5%, and for metal, more than 98%. So now, before I hand over to our additive manufacturing team, just want to give you an overview of what you will see over the next 5 minutes or 10 minutes in the additive center. And it is our, in my view, very fascinating and highly scalable print, wash, and sinter process. So that's it from my side. I hope you have fun with the team from the AM Center. I hand over. Thank you very much. And
thank you, Stefan, for the introduction. Now it comes to the most interesting part of this webinar. We'll connect from our additive manufacturing center, and Ron, the team leader, will guide you on the tour at our facility and show you how exactly we printed this nozzle. And before we start, I would like to remind everybody that if you have any questions, simply drop it in the Q&A box. Don't hesitate to drop it anytime that the spirit comes to you. So now, Ron, the floor is yours. Are you ready?
Hi, guys. How are you? Thank you for joining me for the virtual tour. We are now going inside the additive manufacturing of XJet to see how we produce parts, actually the most interesting parts in the world. So we are inside the additive manufacturing center. I am Ron, the manager of the AMC, and follow me to see the story of we are manufacturing some parts. So actually the story starts for the tray design. So let's design it together. We are seeing now the part that Andy mentioned earlier. This is the nozzle part. And now we are going to just duplicate it. By the way, we can either print many different parts, or we can take a single part like the nozzle and duplicate it in multiple copies. So now we are going to duplicate it. Let's duplicate it in y-axis and in x-axis. Computer is thinking, and that's it. Okay. We have the parts. We left only with the recipe selection. The recipe is our option to produce parts with different model and support mixture. For example, it will support during the support removal or the sintering. We can create a complete model as a support to support during the sintering stage, or a pure support that will be helpful for internal channels. In this case, the part is pretty easier for our technology. So we will select the standard recipe and we will select build. Now we are heading over to the most interesting part. We are going to start the job actually, and we see how we are direct jetting both model and support simultaneously, as Stefan mentioned earlier. So how the technology works, we are direct jetting both model and support materials. That our ink is made of nanoparticles, so we are direct jetting both model and support. Let's start the job. So we just press run and start the job. So let's open to see how the story starts. So what we are going to do, we are going to start the job, and we will see how we are direct jetting both model and support. What we are doing, we are jetting on a hot surface the liquid, and all the liquids are evaporating. So we will stay only with the model and the support. So let's see how it goes. So we are printing layer by layer. Every layer is about 8 to 10 micron. And you can take a look how we can start the job. It's the initial process. It takes 1 minute to start the job, and we can see the process starts. We can see how environmental friendly the process, so we can actually open the window and come closer to the moving printers. And now I want you to follow me to see the same job that we started earlier, and it's about 1,000 layers already been printed. It's again the same nozzle that we mentioned earlier, and you can see after 1,080 layers been printed. By the way, we are direct jetting only on demand on the desired shape, almost near net shape. And now I want you to go with me together to see how we perform the support removal. So I want you to come with me, and Aviv, which is one of our expert engineers, to perform the support removal. You can see this tray is the same tray that printed and complete. So we completed this tray. The same nozzle parts. You can take a look how amazing the parts are. And what we are going to do now, we are wash those parts upside down. So we'll put the tray inside the water, and then we are waiting for the water to stream and to remove the support. As you know, our support is soluble, so the water will wash away the support. We are adding some jacuzzi to this process to keep it, to put it a bit faster, and actually to be more comfortable for the parts. And so what we are going to do now, we will leave the parts inside the smart system, and we will see actually the most interesting parts. We will see the parts itself after the producing. And our parts are amazing. The accuracy and the surface roughness are amazing. The accuracy is between N9 and up to N6, which is very smooth. And thanks to our automatically support build structure, we can, and our soluble support, we can print very complex geometries. And to get the amazing accuracy that we can see here, what we are seeing now, we are seeing a report of a GOM scanner that we performed. And you can see the legend on the right side tells the story. Most of the parts are very accurate in the plus minus 50 micron and up to plus minus 100 microns. And this is, guys, how we produce single, 5, 10s, and thousands of parts every day. So this was the additive manufacturing center. And now I want to give you a sneak peek of our R&D. I want you to see the power of XJet. So follow me to see how many machines we have. We have 9 machines here, and their purpose is to produce and develop new materials, new software, and to enhance our capabilities and to improve. And you can see the XJet muscle here, all those machines here, and the amazing technology. And this is it, guys. This is how we produce parts here. So thanks you guys for joining us, and I am adding the mic to Yael. Thank you, guys.
Thank you so much, Ron, for the brilliant introduction and for the detailed demonstration process. And I hope everybody enjoyed it as much as I did. Now that we have showcased the capability of XJet solution, you may wonder, how could it be translated into business potential, and how could your company benefit from this major shift into powderless additive manufacturing? So allow me to bring back Stefan to the podium. He will present to you the cost per part calculation model and elaborate the economic benefits of XJet solutions. Stefan, please.
Thank you, Yael. Thank you, Ron. Fantastic presentation. So just one quick slide about the productivity to show you the dimensions of what we can print and on what we print. So in terms of productivity, we print at around, and this is based on the precision of the printing job, 0.7 millimeters per hour. The layer thickness, as we mentioned, is at around 8 micron. A tray size, the one that you just saw, is at 500 times 140 millimeters. And the maximum part size, and it's subject to design rules, of course, but we always can stretch in any kind of direction, is 200 times 107 times 60 on ceramic, and on metal, 200 times 107 times 30. So how does this translate into our fantastic multi-input nozzle? As you saw, the tray that was designed for this presentation and also for the print job that Ron just showed you was stacked. That means that we have multiple layers of parts. And because of the support that we print in parallel, we even have the chance of creating three-dimensional stacking. So the parts themselves are not just on a separate layer, but are even interlinked with the first layer. This would be, for example, relevant or necessary if you have issues with, in terms of volume of resources, human resources, to support one whole system. So you can print multiple layers over the weekend, overnight, and don't need too many resources. But for our part, my cost per part calculation, so the economical calculation for this part, is what you can see here. It's a one-layer print, so not stacked, and that shows that we can print 152 parts on one tray that you just saw. The time for one printing for one tray is at around 200 hours. And now the best for last, and we kept this as a little secret to ourselves. It's not just 10,000 of these parts that we can actually print per year. With an 80% system utilization, we can print at around 6 to 7 trays per week, 50,000 of these nozzles per year. And the total cost per part is at around €6.50. If you have any questions about this calculation, go ahead in the Q&A or contact me. So I will hand back to Yael. This is it for me. Thank you very much.
Thank you, Stefan, for the introduction, for the explanation. We see that there are questions in the chat bar, so we're going to answer them. First question is that, are you able to communicate the exact grain size you're using for ceramics and metals? And how easily can you change the recipes of the material? During the support removal, the parts are not sintered. How do you manage the water not interact with water? Is it drying stage? So here, I'm going to bring up Andy to answer these questions. I'm sorry for the noise here. So Andy, please go ahead.
So firstly, thanks to the team for walking us through it. Just coming back to what Yael said, there's a couple of questions that have come up. You know, do we have to sinter the parts? Is there a drying time? Yes, of course. And I'd just like to hand over to Ron to walk you through what does the drying, after washing, what does the drying and the sintering really mean? Ron.
Yeah, so actually, after the support removal is done, we need to remove the water that stays inside the parts. So we dry the parts in an ambient environment. This process takes overnight to up to 20 hours.
And then when we go into the sintering oven, what sort of sintering times do we need to calculate with, Ron?
Yeah, the average sintering profile takes about 40 hours.
Okay, and this is a standard commercially available sintering oven?
Yes, standard commercial.
Perfect. Okay, great. Any other questions coming in, Jan?
There are questions about debinding time, how to avoid warpage of the ceramic part when sintering.
So the debind time is together with the sintering time. It's a single step. It's together and it's about 40 hours. So including the debinding. So yeah, we talked about it during the show. We have a support that helps us during the sintering stage in order to support the deformation and to reduce or remove completely the deformation. So what we are doing, we are printing both the part and the support as a model or a predefined model that designed before. And we are sintering the part with the support as a model together.
Thanks, Ron. Thanks, Ed. Okay, I think that's covered most of the questions. Let me just now try and, if I may, Oh, sorry, just one more just
There's
come in.
one business question.
Excuse me, one moment.
Do you do small productions for external companies, and are you planning to set up a production plant in Europe?
Okay, the question is, do we do production for small companies, and are we planning to set up a facility in Europe? Here at the AMC, the Additive Manufacturing Center, we is primarily here to prove the part and do the benchmark and test capability and performance. For those of you who may have a requirement for small runs of production, we don't do them here at our facility. However, we do have sites within Europe and in Germany who will be happy to fulfill those requests. I'm more than happy to share those details to the audience by mail after the call. Okay, I'm just checking. I think we're good for the questions now. Okay, one more question we get. I'm sorry, gents, there's one more question just coming in. Ladies and gents, excuse me. Okay, we'll just take this last one. Ron, I'll give this one to you. What are the XYZ shrink rates?
Yeah, so our shrinkage is isotropic, and it varies between different materials. It's between 15% up to 17.8% in the zirconia.
Great, Ron. So we're going to have to hold the questions there. Of course, Jan will be giving you some contact information after the session is closed. But just to reiterate what Ron said, our parts are isotropic in terms of shrinkage, and the average shrinkage, depending on the material, is between 15 and 17%. Thank you, Ron, for that information. So, ladies and gentlemen, I'm just checking the timing. We're actually absolutely bang on time. I'd just like to share with you a quick summary of my thoughts about XJet and its role within the additive world. As you've heard, XJet is a high-tech company based here in Israel. We have our global go-to-market and marketing and customer support departments to service our customers and also to advise our customers. For many of you, looking through all the multiple technologies which are out there claiming to be, the best in class for 3D printing, it's a pretty tough job for you to find out what the truth is, beneath the noise. Our position within that market, and I firmly believe it, being quite comfortable on most available technologies today, is that we are the only company that have broken the code to actually move from 3D printing where it was, which was mainly prototyping, design verification, into full production. If you're looking for a system to produce prototypes, it's not XJet. If you are looking for an additive manufacturing system for ceramics and metals to go into production of high quality parts with a clean and safe system, powderless, and having the unique capability of, as Stefan pointed out earlier, soluble support, which is the key benefit of our process, then you should be talking to XJet. And the fact that you've joined us on this tour, that you're eager and willing to learn about the technology is really fulfilling and very warming for all of the team here. So with that, I would like to firstly thank my colleagues within XJet for pulling this together. I would also like to thank all of the staff that were involved in the preparation, but more importantly, or as importantly, I'd like to thank all of you for taking 45, 50, 60 minutes out of your busy schedule to attend this. I'm sure, as often behind some of these tours, that the real questions come later, once you've had a moment or a few hours to digest what you have heard. That's our job, to be there for you, to guide you through the jungle of 3D printing and additive manufacturing. And with that, I'd like to say to all of you who've spent time with us, thank you very much. Have a wonderful week, and best regards from Israel. Thank you so much. and goodbye.
Thank you so much. And Andy actually took my conclusion remarks. I prepared a page of conclusion remarks and he just took over, but it's very well said. And again, thank you everyone for participating. I see that there are 1 or 2 questions that we haven't answered. So Stefan will make sure that all the questions will be addressed. And if you have any further questions, please don't hesitate to contact us. And I'm sharing the contact info here. Just if you take interest in marking them on your contact information or like to reach out later on. As you have noticed, we already recorded this session and we'll share it with everyone who has participated today. So if there is anything that is not clear, or if you would still like to go over the session, you still have the chance to do that. Okay, so I guess we are good for today, and I hope it's a successful and fruitful session for you. We'll have more activities, including virtual open house and including offline open house even. So please stay tuned to our social media page, to our website. We have a lot more coming up and we can't wait to share with you. So thank you everyone, and have a good day. I hope to talk to you soon.